Hey there, in this video we are going to look at graphs of basic exponential functions and investigate some of their features. To start looking at graphs of basic exponential functions, we're going to use two that have fairly simple numbers that are easy to work with. Y equals 2 to the x, y equals a half to the x. We'll look at what the graphs look like, some of the features, and then we'll generalize from there. But before we put it down on paper here, we're going to look at it using Desmos. Now before we graph the curves here, we're going to start by creating tables of values like I had on my other page. So we're going to work with 2 to the x first, so we can put it in here. And we'll start with probably the easiest value to think of mentally here, which is 2 to the 1. Now it's going to work it out for us, but 2 to the 1 is 2, right? And then if we go 2 to the 2 is 4, and if we go 2 to the 3 is 8. Right, and we've got those 3 points on there, right? 1, 2, 2, 4, 3, 8. And I could continue going there, but what I'm going to do is I'm going to go the other way because we want some values on this side as well. So to do that, I need to make a few more spaces here. I'll do that. I'll put the 1 in there, and I'll get rid of that one. Now, if we continue the other way here, we've got, of course, 2 to the 0. 2 to the 0 is 1. That's where it crosses the y-axis. If I continue my pattern here, 2 to the negative 1 is 1/2, 0.5. 2 to the negative 2 is 1/4, 0.25. And just to make it symmetric here, we'll go 2 to the negative 3. 0.125 is 1/8. And as you likely know, the relationship between these values negative exponents and these values positive exponents, these are reciprocals. 2 to the 1 and 2 to the negative 1 are reciprocals. 1/2 and 2 are reciprocals. 1/4 and 4 are reciprocals. And 1/8 and 8 are reciprocals. So that's what that graph looks like. Now if we put the curve in here and look at it, y equals 2 to the power of x. It's going to pass through those points, of course. Now you notice a few things about this. First of all, we said it passes through this point 1, 0. That's its y-intercept because 2 to the 0 is 1. Other things you notice here is it behaves differently on the right and the left. On the right side, that's just going to keep going up and up and up. It's going to keep getting steeper and steeper and steeper. It's not going to go completely vertical. It's always going to move to the right, but in a steeper and steeper fashion as you go. Our next point in here, if we put 4, 2 to the 4th is 16. It would be 4, 16 right up there. And then 32, 64, 128. As it goes to the right, you can say as x gets bigger and bigger, or what people say is as x approaches infinity, as it goes to the right towards positive infinity, the y values also go upwards towards positive infinity. As x approaches infinity, y approaches infinity for this graph. But on the other side, that's not what happens. As you see what the shape of this graph looks like here, as you go in the negative direction, as x gets more and more negative here, these are getting smaller and smaller. If I trace along the graph here, you can see that those y values are getting smaller and smaller and smaller. They're still positive. They're still above 0. They're not actually getting to 0. And if you kept going to the right here, you're going to find that it's going to keep getting smaller and smaller. It starts to say 0. But that's because this program is rounding it off. It's always going to be above 0. If you think about it, 2 to the power of however negative of a number you can think of there, it's going to be 1 over some positive number. It's always going to be a positive number. So as you go to the left here, this graph gets closer and closer to 0 but doesn't ever get there. This behavior on the left here is different than the behavior on the right. On the right it was as x approached infinity, y approaches infinity. As you go to the left, as you go towards negative infinity, as x approaches negative infinity, the y values approach 0. They get closer and closer to 0. All right, that's what happens with that function there, y equals 2 to the x. Now let's have a look at 1/2 to the x as well. Now it's going to fill the table out for me as soon as I put this function in here. And so you can see, now you might be able to make some predictions about what that is. Now I haven't put the x in there yet, so it just says 0.5 for everything, but there's those values. If you notice, those values are just the same values here, just in the opposite order. 2 to the 3 is 8. 1/2 to the 3 is 1/8. a half to the 3 is the same as 2 to the negative 3. You know that negative powers are like reciprocals, so it makes sense here that 1/2 to the positive 3 is the same as 2 to the negative 3. And all the way down the list, the same thing. 1/2 to the positive 2, same as 2 to the negative 2, and so on, right? So these points are just the same values, but in the reverse order. And so what that means is when you look at the graph, they're going to go the opposite way like that. All right, so when you put this curve in here, y equals 1/2 to the power of x, then we see that that graph looks like that. Now, it's actually the same shape as this other graph. It just has the opposite behavior on each side. For this red graph, as you go towards positive infinity, as the x values get larger and larger, as x approaches positive infinity, the y values approach 0. Again, if you trace along here, those y values are going to get smaller and smaller, but they're never going to become 0. As x approaches infinity, y approaches 0. As you go the other way, as x approaches negative infinity, the y values approach infinity. They go up and up and up for the same reason as they do on the other side there. All right? Now you probably noticed that those are mirror images of each other across the y-axis. Now you're going to see later on why that is and how to show that that is true algebraically. For now, we'll leave that. Now this behavior where a curve gets closer and closer to a line, for both of these graphs, this curve gets closer and closer to the x-axis, or in other words, what you call the line y equals 0. The line y equals 0 is called an asymptote for this graph. An asymptote is a line that a graph gets closer and closer to, but doesn't ever actually become that value. So for this graph, the line y equals 0, that purple line in there, that line the two graphs get closer and closer to, but don't ever get there. That's called the asymptote for this graph. In this case, it's a horizontal asymptote. You could say that these graphs have asymptotic behavior around there, along that line. And that just has to do with the fact that these values get smaller and smaller one way or the other for these functions. All right, let's go and summarize some of that now. All right, so there's those two tables of values and the two corresponding graphs. Now this table had some more spaces in it, so I added each of them x values 4 and negative 4 in each case there, and you can see that those points can fit on that graph as well. So to summarize some of the things we saw about that, what happens to each of the graphs, the y values, as the function gets bigger and bigger without bound? Now I put absolute value here because we don't care. We're looking at both directions here. We want to know what happens as you go, as x gets bigger to the right or as x gets bigger to the left. And we found that one direction, the y values approach infinity, and the other way, the y values approach 0. Now it's different for 2 to the x and a half to the x, but both functions do each of those things on one side or the other. And we said that that is called asymptotic behavior around the x-axis, or you could say that the x-axis is a horizontal asymptote for that graph. Now, if you're thinking about some of the features of the graph, the domain of this graph, the domain is all real numbers for both of them because we could put any value we wanted in there for x. We chose numbers that are easy numbers, but you could choose any number you want. This is going to go all the way to the right and all the way to the left. Even though it's curving up, it covers all the x values. Both of those graphs do. But something you also notice there is that the range is always positive numbers. We saw that no matter how far we go one way or the other in the table, these are just going to keep getting smaller and smaller, but it'll always be positive numbers, either to the left or to the right. And because of that, the range of these functions is y is greater than 0. We said that the asymptote was the x-axis. You can write that equation as y equals 0. Both of these graphs have the y-intercept at 1 because something to the 0 is 1. Regardless of what the something is, anything to the 0 is 1. So both of those have a y-intercept of 1. Whereas x-intercept, as we said, since the function never gets down to 0, there is no x-intercept. All right? And then the behavior. So first of all, the behavior as you approach infinity. Now you may never have seen this symbol before, but this x and then an arrow and the infinity symbol means as x approaches infinity, meaning it gets bigger and bigger and bigger without any upper boundary. All right, so behavior as x approaches infinity. For 2 to the x, the y values approach infinity. As x approaches infinity, the y values approach infinity. If you wanted to, you could say that as x approaches infinity, y approaches infinity, if you want to use that same notation like that. And as x approaches negative infinity for that graph, as you go to the left, those values approach 0. They leveled off, right? And again, you could say y approaches 0 if you want to. And then for a half to the x, it was kind of the reverse, right? As x approached infinity, as in to the right for the half to the x graph, that's the side that the y values approach 0. And again, you could say y approaches 0. And then that graph, when you went to the left, it was kind of the reverse. So that's where those graphs went upward towards infinity. And again, of course, you could say that. All right. Let's move on and look at something else. All right, we're going to look a little more generally at things now. The function y equals b, some number to the power of x. And we're going to split it into 2 groups here along the lines of what we did in our first example. We're going to look at numbers like y equals 4 to the x, 6 to the x, 9 to the x, or in other words, values where the value of b, that base, is greater than 1. And then we're going to look at things like 1/3 to the x, 1/5 to the x, 1/8 to the x, b values that are less than 1. But again, before we write it down here, we're going to look at it on Desmos. Okay, we have here the 6 functions that I had on that page. 3 of them where the base is bigger than 1, 3 of them where the base is less than 1. And hopefully from our first example, you know that 4 to the x here, this is going to be going up to the right like this. And the reason is because as you pick bigger and bigger x values, 4 to the 1, 4 to the 1 is 4, so that point is going to cross there at 4. Well, let me put it, there we go. 1 is 4, 2 is going to be 16, 4 to the 2 is 16, 4 to the 3 would be 64, would be way up there, and they would just keep getting bigger and bigger. If we go to an even bigger base, then you might be able to predict that's what's going to happen there for this one, because 6 to the power of something, 6 to the 1 is 6, which is obviously bigger than 4, so that curve is going to be higher up like that. And then 6 to the 2 would be 36. That's why you can't even see it getting over to this value of 2. And then for the same reason, when you go to y equals 9 to the x, 9 to the 1 is 9, so it crosses right in there. And then 9 to the 2 would be 81, so way up there, right? So the bigger that base is, the steeper it is as it goes up to the right. It's hard to see what happens to the left, but for the same reason here, those values are going to be different. Actually, the highest up one on the left is going to be that blue one, because 4 to the negative 1 is 1/4, whereas 6 to the negative 1 is 1/6, and 1/6 is higher than 1/4, so that's going to be 1/4. But then when you're on this one, 1/6, whether it lets me stop there or not, that's what 1/6 is as a decimal, a smaller value. And then this one, same reason there. That's going to be 1/9. Negative 1, 1/9. So the green one, the higher the base, the steeper it is going up to the right, but the quicker it heads down towards the x-axis there. Now, if we look at the other 3 where the base is smaller than 1, as you might have predicted from our first example, they are going to do the opposite. They're going to go down to the right when that base is smaller than 1 like that, because 1/3 to the 1 is 1/3. 1/3 to the 2, 1/3 squared is 1/9. 1/3 to the power of 3 is 1/27. 1/81. Those values are getting smaller and smaller as you go to the right. And then since negative powers are the reciprocal, 1/3 to the negative 1 is like 3 to the positive 1, so it's a 3. 1/3 to the negative 2 is like 3 to the positive 2, 9, etc. And then as you make these values smaller, 1/5 is smaller than 1/3, it happens in a more steep way, just like it does on the other side. 1/5 to the 1 is 1/5, so this point in here is going to be 0.2, 1/5, whereas on this curve, right, it was 1/3, right there. Right, so it's lower down on that side, but higher up on this side. And then the third one, same pattern there, right? 1/8 is even smaller than 1/5. So it's going to go down more sharply here because you're at 1/8 here. And then you're going to be 1/64 here, and so on. And then as you go to the left, those values get bigger and bigger there, right? Because 1/8 to the -1 is 8, right? So this one's going to cross at 8 there. And then it would be 64 and so on, right? Now to see this a little bit more dynamically, I'm going to turn off all of these. And I've created a function with just a b in here so that it's a variable and a slider that I can manipulate there. So right now that is the graph of y equals 3 to the x because b is 3 down here. And as we saw before, the bigger I make this, the steeper it goes up to the right. Right? If you're watching the right side of the curve, the steeper, quicker it goes up towards infinity. But on the left, the quicker it goes back down to 0. So if I put it in there, it's taking its time to get down to 0, right? It's a nice shallow curve down to 0. But you make this bigger and bigger, it's more quickly going down to 0. All right, so base bigger than 1, it goes up to the right, and the larger the base, the steeper that curve is. Then we go on the other side here. When this is less than 1, right? This is less than 1. It's going down to the right, and the smaller it is less than 1, the sharper that turn is going down to the right. All right, 0.1, 1/10. That's pretty steep going down there. This -1 would be 10, and 1 would be 1/10 there. All right, so base bigger than 1 goes up to the right, base smaller than 1 goes down to the right. But some things they have in common, of course, are the x-axis is an asymptote for all of them. They all have that horizontal asymptote there. They all have this y-intercept of 1 because anything to the power of 0 is 1. They all have a range that is the y values are all greater than 0. They all have the domain of all real numbers because you can substitute any number you want in here for x into any of these. There's no restrictions on what you can put in for x, so the domain is all real numbers. All right, now you might have seen in the middle there, I skipped over pretty quickly, but what if the base was equal to 1? I've talked about bases bigger than 1 and bases smaller than 1, but if it's equal to 1 there, it's just a horizontal line. Because 1 to the power of anything is 1. No matter what the x value is, the y value is always 1 there. All right, let's go back and summarize some of this. Now there's those graphs that you saw, and what we were looking at is how does changing the value of b affect the graph? Well, first of all, that makes the graph more or less steep on one way or the other, changes the steepness of it. They go up to the right if the b value is greater than 1, this way, and they go down to the right if the b value is less than 1. All right, like that, those ones. And of course, they do have some similarities and some obvious differences there. Some similarities between all of these. They all have a horizontal asymptote along here, y equals 0, the x-axis. They all have the domain of all real numbers. You can substitute anything in for x, and you get a y value. They have a range that is y is greater than 0 because you can't get 0 and you can't get negative numbers no matter what you put in for x. That graph never crosses the y-axis or goes below. And one last similarity here, they approach infinity one way and 0 the other. The ones with a b value bigger than 1 approach infinity on the right, 0 on the left, and the ones with the b value less than 1 approach infinity on the left and 0 on the right. And then maybe a more visual way to think about that is those graphs go up to the right if the b value is bigger than 1, and they go down to the right if the b value is less than 1. And we saw if the b value was equal to 1, that graph would just be this horizontal line, graph right across there at 1 because 1 to the value of x is always 1. And then before we leave this here, say what would that graph look like? 3/2 to the power of x. Well, the first thing to recognize is since this value is bigger than 1, it is going to go up to the right, but it's not going to be as steep as 2 to the x or 3 to the x or anything like that, because this value is only 1.5 to the x. If you wanted to think about some points, well, that y-intercept is going to be 1 because anything to the power of 0 is 1. But then at 1, the y value is going to be 3/2, 1.5. And similarly on the other side here, at -1, it's going to be 3/2 to the power of -1 is like 2/3 to the power of +1, that reciprocal, so 2/3 there. And then if we're going to the right even more, 3/2 squared, 3/2 to the power of 2 is 9/4. All right, so that's generally what that graph would look like. All right, and now let's kind of summarize all the ideas we've seen here together. All right, so summary of features of the graph of y equals b to the x, that basic exponential function. We saw that this has no x-intercept because that graph never crosses the x-axis. It doesn't ever hit 0 and it doesn't ever go into the negatives. Whereas it does have a y-intercept. It always has a y-intercept of 1 because anything to the power of 0 is 1. And we saw that related to the fact it doesn't have an x-intercept is the fact that it has an asymptote, a horizontal asymptote, the x-axis, which the equation is y equals 0. It has a domain of all real numbers because any x value is possible, whereas the only y values that are possible are the positive ones, greater than 0. In general, the shape of the graph is different depending on the base b. If the base is bigger than 1, it goes up to the right like this. If the base is less than 1 but still positive, like that, that's the way you say that, then the graph goes down to the right like that. And in general, as the base becomes larger and larger above 1, that graph becomes steeper and steeper uphill, right? It goes from that to that, the bigger that the b value is. And as the b value becomes smaller and smaller below 1, the same thing happens in reverse here. It goes from this to this, becomes steeper and steeper downhill like that as the b value gets smaller and smaller. All right, so that's a look at basic exponential functions, y equals b to the power of x.